Okay, so version 8.1 of the Tycho software has just now been released, and the first item on the list here is that it offers an improved alignment routine. So what this means is that you can have a set of images, even with a meridian flip occurring throughout the acquisition period, and it will align them with no issue. It now also offers the ability to apply distortion correction, and I will go over what that means in more detail in just a moment. But the next item on the list is we also have the ability to stack a set of images on an object having variable motion. So the object could be moving with nonlinear motion, and we can still extract detail from that object. And finally, there are also a number of enhancements made towards the photometry aspect of the software. So before I go into the details on all of these enhancements, I'd like to first just take a moment to summarize some of the discoveries that have been made in the past month. And these are discoveries of near-Earth objects, near-Earth asteroids in particular. So what you can see from this table is that the past month has been really busy with discoveries between these two observatories, W16 and W94. So W16 is out of Alabama in the United States, and W94 is out of San Pedro de Atacama in Chile. And so between these two amateur class observatories, a total of 11 near-Earth objects were discovered just in the past month. So this is a record-breaking month for the discoveries. Again, these are amateur class observatories with amateur class equipment. W16 has two C14 telescopes. These are 14-inch Schmidt-Cassegrain telescopes in hyperstar mode, and W94 has two 11-inch or 28-centimeter RASA telescopes. RASA meaning Roe Ackermann Schmidt astrograph. So basically 14-inch, 11-inch aperture, metric being 36 centimeter to 28 centimeter aperture. So that's amateur class, and again, these discoveries are quite exciting. Not too long ago, people would say that the days of amateurs making discoveries were long over. But as this table shows, that's really no longer the case. So the first column, you can see the designation of the object. You can see the observatory that made the discovery, the date of the discovery, absolute magnitude, and so forth. So I'd also like to show just briefly kind of what the orbits of these objects look like. I think that's kind of interesting. Okay, so this is the CSS Orbit View program written by David Rankin. He did an excellent job of implementing all these features to make it a nice, easy to use tool to visualize the orbits of asteroids. So what I'm doing here is I've loaded up all of the 11 discoveries from the past month. And so I can navigate from one to the next, and you can see its orbit plotted in the viewer. So the other thing I can do is I could also do a show all. So this will show all of the orbits at once. So again, it's a great way to visualize different asteroid orbits. You can pan, zoom, tilt, and it's just, I like to use it. And this certainly has a way to show that these are definitely near-Earth objects, just due to the fact that they do come in close proximity to the orbit of Earth. So if I wanted to, I could hide the names and kind of clean up the display here. We could also hide the orbits, and so you can see this sort of this cluster of near-Earth objects, again discovered fairly recently within a short time frame of each other. So it's pretty cool, I think. Again, synthetic tracking was used to discover each of these objects, and again, I think that just shows that it's still in its infancy. It still has a lot of potential, and it's definitely proven itself because these are all made with amateur class instruments. And in fact, there is one object on the possible comet confirmation page, which may turn out to be the first comet ever discovered using the synthetic tracking technique. And so if that's the case, that would be very cool indeed. So Now let's go ahead and go back to the updates for this version of Tycho. Okay, so as I mentioned earlier, one of the main enhancements with this new release is the improved alignment routine. So what I have done here is I've loaded up a set of 60 images, the first 20 of which, if I zoom in a bit, you can see the offset from one image to the next. There's just a little bit of offset, but you can see that they are certainly not yet aligned. And then as I get to the 21st image, then you can see that a meridian flip has occurred. So if I zoom out a bit, you can see this these three main stars form sort of a triangle, and then as I get to the next image here, you can see the meridian flip has occurred. So there's been a large rotation, and basically the previous version of Tycho just had kind of an issue dealing with that, but now that has been fixed with version 8.1. So let's go ahead and take a quick look and see how it performs in this condition. So I'm going to go to Action, Align Images, and I'm going to choose the internal routine and the settings for this. Because these images were taken with an instrument that does not really have any distortion, then we can go ahead and choose the fastest mode. And the stars are not saturated and there's enough stars, so we don't have to choose the normal mode. There's fastest and then there's normal. So fastest mode works when you have a sufficient quantity of well-defined stars, and that's what we have here. So I'm going to choose fastest, and as I go ahead and click OK, then you can see it work through these 60 images. So again, it's very fast. It's still going to warn you if there is a meridian flip, just in case you do have an instrument with distortion, then you might need to use the other mode. But let's go ahead and take a quick look and see how this performed. So I'm going to go ahead and load up the output and inspect the images. And so if I zoom in a bit, then we can see how well the alignment behaved. So I'm scrolling through all 60 images, and as you can see, the meridian flip had no issue, no impact on the alignment. And let's go ahead and go look at a corner just to see, because that's where you will typically have most of your issues near the corners of an image. So as I scroll through the images here, the stars are still very well defined and well in position. So this is a nice improvement because now you don't have to use an external alignment tool to perform this step of the processing. Now, if your telescope does have a noticeable amount of distortion, which is commonly the case with a refracting telescope, then you probably will want to enable the distortion correction option. And so if you're curious to know how this works in theory, then what I've basically done here is I've implemented a technique that makes use of thin plate splines. And so other programs, PixInsight is one, and I believe Registar is another, they use the same technique where you essentially construct a distortion map, and these thin plate splines are essentially an interpolation tool. And so each control point in this map essentially defines the amount of distortion at a given XY coordinate in the map. So at this XY location, you might have a little bit of distortion. At another XY coordinate, you might have a bit more distortion, and so forth. And so the formula for this is that given an XY coordinate, you wish to compute the amount of distortion at that location. So you have the A1, A2, and A3 coefficients, and you can see that X and Y have an impact on the computed distortion. And you are also computing a summation. This is a weighted sum that makes use of the control points that you have computed and constructed across the image. And so each control point, you compute its distance to the input coordinate, and that in essence is going to play a part into its contribution to the distortion map. And so if you want to know a little bit more about the theory, I have a link to it here. There are other resources on it as well. But essentially you actually compute two distortion maps, so one for X and one for Y. So given an XY coordinate, you compute the distortion in the X component, and for that same XY coordinate, you will compute the distortion for the Y component. And so these are two distinct distortion maps, And so again, the theory behind it is actually fairly straightforward, but the way that it is implemented can be a bit tricky. In this example, the control points would be the stars in the image, and so you want to make sure that when you extract stars from the image that you are not extracting hot pixels or other camera artifacts. And if there is a lot of distortion, then it can be tricky to know that you are associating the correct star with the corresponding star in the reference image. And so that's what made this a bit difficult to implement, but I've tested it on a number of different data sets and it appears to work quite well. So let's go ahead and take a quick look at an example. Okay, so in this example, I have two images that were taken with a 127mm refracting telescope. So if I click on one image and then scroll to the next image, you can see that there has been a meridian flip occur. And because, again, this telescope does have a noticeable amount of distortion, if we align these images with the default mode without distortion correction, so I'm going to go to the normal mode of operation, then you should notice a noticeable, again, distortion in the corners of the aligned images. So let's go ahead and take a look and see what that output looks like. So I go ahead and load up the output here, and then you'll see the result. This is the reference image, and this is the image number 2 that was supposed to be aligned with that. So if we zoom in a bit, then you can see that the stars do not match up as well as they should. And again, that's due to the distortion. Now, if we go to the center of the image, it's not nearly as noticeable. You could almost be mistaken to think that they are aligned, but again, it's more in the corners where you have the issue. So what you have to do in that case again is that's where distortion correction is necessary. So I can go ahead and animate the images here, and you can kind of see that again, the distortion. So let's go ahead and try it again with distortion enabled, with distortion correction enabled. So I'm going to go ahead and go back to the original unaligned images, and this time we'll go to this option here, enable distortion correction. I click OK, and it will take a little bit longer to align these images with that feature enabled, but that's one downside to it. It does take a little bit longer to process the images, but if you have a scenario where you need to use it, then that's the end result. So this is the output. So let's go ahead and animate these images as we did before. And this time you'll notice that the stars match up even in the corners. So it's very nice. The alignment works quite well. And so this is, again, what you would have to do if you have distortion. Now, one reason that I might advocate against using distortion correction is whenever you have a slow moving object, or whenever you have a sequence of exposures that are short in duration that would make the object appear to have slow movement, then the distortion correction algorithm may tend to mistake its motion for distortion. In other words, it might treat that object as a control point. And so I have an example of that here. The crosshairs are centered on an asteroid, and you can see the magnifier is zoomed in on that asteroid. So for the first 9 exposures, you can see that there is very little motion. As we look at it in the magnifier, there's very little motion of the object in these first 9 exposures. And then as we get to exposure number 10, you can see a noticeable jump in movement. Even though these exposures have the exact same duration and they have the exact same delta time between them, there is a noticeable jump in movement from exposure 9 to 10. And this is not unique to the Tycho implementation. This is actually what you're looking at here. These images were aligned using the PixInsight implementation. So this is a generic artifact of distortion correction in general, because what it's doing is it is mistaking the motion of the object for distortion. So for these first 9 exposures, it's trying to keep the object in its original position. And then as it gets to exposure number 10 here, the motion, the position of the object has moved sufficiently away that it is no longer being forced into that original position. So it's beyond that threshold. And then as we go to the other images, you can see it has resumed the normal motion. So whether or not this is a major issue depends on the application in question, but basically it's just something to keep in mind. It's something to consider, that this is again a generic artifact of distortion correction. It may not impact, in fact it really will not impact all asteroids like this. This is definitely just one example, but if the object is sufficiently bright enough, then it will be extracted as a control point. And if it has basically this sort of motion, then again there is potential for this to occur. And so again, it may be a minor issue, but something to consider. Now, if it were me, probably I would just simply not enable distortion correction unless the telescope really has noticeable distortion and requires it in the first place. So basically we have 3 options. So you can go to Action Align Images, and for the settings you have 3 different modes of operation. So you have fastest mode, you have normal mode, and then you have normal with distortion correction. So again, I would probably only check this box if the telescope really has noticeable distortion. Otherwise, I would leave it unchecked. And if you're wondering what the difference is between fastest and normal, let's go ahead and take a moment to look at an example where you would use normal mode of operation. Okay, so the brief difference between the 2 modes of operation. Fastest mode will work whenever you have an adequate number of well-defined stars in the image, whereas normal mode will work even if you do not. So normal mode, basically, when in doubt, use that. It will almost always work, even if the stars are saturated. So in this example, we have a set of images where there are very few stars in the images. So we have just these 4 stars, and there's also 1 star up here. But basically, this is kind of an extreme example. So let's go ahead and see what it would look like if I were to use the fastest mode. So I go to the internal tab, and I'm going to choose fastest, click OK. And again, fastest mode should not work in this example because there are very few stars. And you can see that it's already kind of complaining. It thinks that there is a meridian flip, but in all actuality, it's just because it was not able to adequately determine the rotation due to the lack of stars. So if I go ahead and load up the output images here, and I go ahead and animate the frames, then you can see that this was not a good alignment result. So in fact, other alignment programs would simply refuse to align these images. I tried it with Registar, tried it with PixInsight. Neither of those programs will work on these images. But if I use the normal mode of alignment, so I go to normal alignment, and I'm not even using distortion correction, I'm just clicking normal mode. Then I choose OK, and we'll go ahead and give it a moment to again align these images. Normal mode is a little bit slower, as the name would imply. It's not the fastest mode, but it is more robust in general. So again, it will work even if the stars are somewhat saturated. So let's go ahead and give it a moment to finish up. And that took 15 seconds to do 56 images, so it's still relatively fast. And let's see how it did. So I'll go ahead and animate the frames, and now you see that they are fairly well aligned. Now there is an image or 2 that has some sort of an artifact on it. So if you notice that if I scroll down here, this is actually just the image itself. It looks like maybe the mount, somehow the mount was bumped or something, so it caused the stars to be doubled up on that exposure, but it still attempted to do an alignment. As you can see here, it chose to align on that reference star. So it's not the fault of the alignment, it's just that particular exposure. The stars were doubled up. And so anyway, that's a pretty good result with as few stars as there are in the image. Now let's go ahead and take a look at one other example. So here we have 19 images, and in this case the stars have very poor focus. So if you notice here, the stars are not very well defined. There are more stars in the image, so that's helpful, but the focus is not very good. It's a very soft focus. And so that means that it would be very difficult to compute the centroid on these stars. So again, if I wanted to, I could try it with the fastest mode of operation, and we can see how that's going to play out. If I animate the frames, then again we have a very poor alignment result. And then I try it again with the normal mode of operation, and it should be able to align it even with this subpar focusing of the stars. So let's go ahead and take a look at that. Animate the frames, and as you can see, it was able to align these images with no issue. In fact, you can see a moving object go across the field here. So it's very nice to see this capability, and again, it's just nice to have this additional option at your disposal. And so again, the idea being now we can handle meridian flips with no issue, and we can even handle fields that have stars that are out of focus, or stars that may even be somewhat saturated, or fields where there are very few stars. So it's a very robust alignment routine. Okay, so another feature that I would like to talk about is the ability to stack a set of images on an object having variable motion. In other words, the object has a non-linear motion, and this is one example of such an object. So I've got 305 exposures here. They are each 30 seconds in duration, and the first 62 images, they were taken one after another, and then there was a gap of 87 minutes. So the first 62 exposures were taken back to back, then we have an 87-minute gap, and then it resumed the 30-second exposures one after another. So as you can see, the object certainly does not move in a straight line. It has sort of an arc to it. It has this non-linear motion, and if you're interested, this object is in fact that of 2020 SO, which is a Centaur rocket booster which was launched in September of 1966. So it's kind of interesting to see that, and I think it's interesting to see it move from throughout a field of view, so to be able to see its movement across a field of view. So what we can do if we want to create a stack on this object, again, that has nonlinear motion, we can first go to Tools, Download Observations. Again, this is 2020 SO. So what we're doing is we're retrieving the known measurements of this object, and then we can view those in Find Orb. So the Find Orb program will compute an orbit, and then we can use that orbit information to attach ephemeris information to the data set. So I double click to then attach that information to each image. So each image has ephemeris information attached to it, and then we can create a stack using that ephemeris information. And so what you can see here is we've now created a stack on an object having nonlinear motion. The arcs are actually the stars in the image, and then the object itself appears as a stationary point from having created this stack. So what we can do now is we can then create measurements on this object. So if I wanted to, there are several ways to do it, but I could select the first third of the images in the data set and then center it and then choose create observation. So I've now created one of 3 observations. I'm going to select the second third of the images, create observation, and then finally the third and final set of images. I'm stacking those as well. So now I have 3 measurements. I'm going to type in the designation of the object, 2020 SO, and then if I want to, I can just visually inspect these. The green crosshairs match up with the centroid of the object. So if I zoom in, you can see that here. And then if we wanted to, we could also compare these measurements with other known measurements on the object. So I can select these, choose right click, view with existing observations. So it has downloaded the observations again, as well as included the measurements that I just made here. So these are the new measurements that we created. And if I were to choose view and find orb, you'll notice, if you pay attention to it, the residuals here on every single measurement are fairly high, and that's because in general when you have an extended arc on an object like this, find orb may or may not compute. It may have some issues with that. So what we can do is go ahead and truncate, in this case, to a set of observations that are closer in time to what we've just created. So I'm going to go to 2020, the end of November as the endpoint. These measurements were, these images were taken in November 25, so that's fine there. And then also remove the front end here. So we now have basically measurements from November 11 to the end of November. And that's going to allow Find Orb to create a finer orbit and allow us to compare these measurements with other observations in that same time frame. So Z84 is the observatory code. So these are the measurements that we just created. And you can see that the residuals are very good. So we have 0.03 for the first one, 0.13 for the next, and 0.15 for the last measurement. So 0.15 being the highest residual, that's pretty good. So if you compare it with other measurements, this is actually a very good set of observations here. So again, this allows you to create stacks again on an object with nonlinear motion. Okay, so to wrap up the video, just briefly, I would like to talk about some of the enhancements that have been made towards the photometry aspect of the software. So here are 122 images. They are each 2 seconds in duration, so they're very short exposures. And what we have here in the center of the field of view is an asteroid. So you could construct a light curve of this asteroid from this data set. And the first thing I would do, you can go to photometry, show photometry stars. And so these yellow, orange rectangles indicate each star that would be, in essence, eligible as a photometry star. And of course, the asteroid itself is not marked as such, so that's why you don't see any rectangle over it. But one thing I've modified is that when you go to find comp stars, you will now see that the photometry stars shown in the overlay will now match up with those that match the filter that you have specified. So you might wonder, okay, why is there a little bit of a gap? You know, why is it not completely uniformly distributed? And that's due to the alignment. So as I scroll through the images, you'll notice that some of them now, just due to how they were taken, there was not any image data on some of these exposures. at this portion of the image. And so it's showing that there's other stars that would otherwise be photometry stars would not make the filter because we have a filter applied on min and max visibility. So if I uncheck that filter and click refresh, then you can see these other photometry stars appear once again. So it's a great way to have some feedback as to what stars are actually eligible to be comp stars. And if we wanted to, another nice feature that's been added is the ability to specify a radius filter. So if I do that, I can check the box here, and also I can right click and choose a marker. So it uses the marker information as the center point of the radius filter. So I can adjust the size of the filter. So if I do this, I click refresh, and then you can see this as a result. So it's another nice feature to have if you want to have more control over the comp star filter. Okay, so that wraps it up for this video. Thank you for watching, and see you next time.